Hi all. In this lecture, I will introduce one of the most important algebraic structures called a group. So before going into the formal definition of group, let me introduce some other concept called a binary operation. So these are the concepts that I am going to cover in this lecture. First, we will define binary operation on a set with the examples as well as counterexamples. Then we will see commutativity of binary operation. Then we will define associativity. Next, as identity element for a binary operation. And finally, we will define groups and we'll see several examples. So let us begin with the definition of a binary operation. So here is the definition. A binary operation star on a set S is a function mapping S cross S into S. So given a set S, a binary operation on that set S is usually denoted by the notation star is actually a function from the set S cross S to S. You may already familiar with the sets and functions, I hope. So given two sets A and B, a function f from A to B is actually an assignment which assigns each element of A to a unique element of B. So here we are considering functions from the set S cross S to S. What is S cross S? It is the Cartesian product. So given a set S, what is S cross S? It is the collection of all ordered pair of elements of S. So let me write set of all AB such that A comma B belongs to S. So any such function is a binary operation on that set S. So let us see some of the examples. We may start with the simple examples. So let us consider the set N, set of all natural numbers. And I am considering the operation addition. What we have to check? I have to check whether it is a binary operation on that set N or no. For that, what I have to check? I have to check whether the operation addition is a function from N cross N to N or no. That I have to check. But this is already clear, right? Because we know that for any pair of natural numbers N and M, their sum N plus M is again a natural number. So their sum is a well-defined number which is unique as well as belongs to the set N. So this defines a function from N cross N to N, which implies addition is a binary operation on the set of natural numbers. By the similar argument, we can see that addition is a binary operation on set of integers, set of rationals, set of reals, and set of complex numbers. Because if you are taking two complex numbers, their sum will also a complex number. So actually, the addition is a function from C cross C to C. So the same argument, all addition is a binary operation in all of these sets. So moreover, I can add one other set, namely Mn of R. Here Mn of R is the collection of all n by n matrices over R. It is the set of all n by n real matrices. Will addition form a binary operation on that set Mn? We know for any two n by n matrix A and B, we can define the sum, right? Also, the sum, since A and B are real matrices, the sum will also are real matrices of order N. That means addition is a function from MNR cross MNR to MNR. That means this defines a binary operation on the set of all n by n real matrices. So next, let us see the operation multiplication. So first we may consider the set n itself. We already know given any two natural number, their product is also a natural number. So this says that multiplication is a well-defined function from n cross n to n. So that means for any pair of natural number, the multiplication is defined, it is unique, and it's again in the set n. So this implies multiplication is a binary operation on the set of natural numbers. By similar argument, we can say that but it is a binary operation on Z, Q, R, and C. Here also we can consider the set M and N. Given two n by n matrices over R, say A and B, I can define the product. So this product will again an n by n matrices. So this product will also an n by n matrices with the real entries. So MNR is closed under this operation multiplication. So here also multiplication is a binary operation on this set also. Now let us consider the operation subtraction. First I am considering on the set Z. So we know that given any two integers, their difference is again an integer. So it's a well-defined function from Z cross Z to Z. Okay, it's a well-defined function from Z cross Z to Z, which implies subtraction is a binary operation on the set of integers. Similarly, it is a binary operation on Q, R as well as C. Now, what about N? Suppose I'm considering the set of natural numbers and I'm considering the operation subtraction on this. Will that form a binary operation? No, right? Because if I'm taking two numbers, say 1 and 2 are elements of the natural number set N. But what is their image under this operation? It is nothing but 1 minus 2. That is minus 1, which does not belongs to N. So it is not, the set of all natural number is not closed under this operation subtraction. So this does not form a binary operation on the set. It's a non-binary operation on the set N. Now for two elements A and B, the image of that pair under the binary operation star, that is star of A, B, is usually denoted by A star. Now we may consider the operation division on different sets. First, I am considering the set of natural numbers. So clearly, this cannot be a binary operation. Why it is not a binary operation? If I am taking 1 and 2, they are elements of n, but their quotient 1 by 2 is not a natural number. It does not belongs to n, which means if n is not closed under this operation. So this cannot be a binary operation on the set of natural numbers. With same example, you can say that it is not a binary operation on any of these sets. I'm sorry. The same example will work for Z. Now, what about Q? So for Q, we know that 1 and 0 are elements of Q. Okay, 1 and 0 are elements of Q. But what about their image of the pair 1, 0 is 1 by 0. But 1 by 0 is not defined. That means this operation is not defined, or Q is not closed under this operation. So Q is also this subtraction division is not a binary operation on this set Q. By this example, I can say that division is not a binary operation on R, and it is also a non-binary operation on C. So finally, let us consider the set GLNR. Here GLNR is the collection of all invertible n by n matrices over R. That is set of all A belongs to M and R such that determinant of A is not equal to 0. Will addition form a binary operation on this set? Clearly, no, right? Because if you are considering the n by n identity matrix, it's a matrix with the diagonal entries are 1 and all other entries are 0. And I am also considering minus in. What will be the sum? In plus minus in will be the n by n 0 matrix, but which is not an element of GLNR. So GLNR is not closed under the operation addition. So this is not a binary operation. So what if we are considering multiplication? Then it will form a binary operation. Multiplication is a binary operation on GLNR. Why it is so? So we are taking any two invertible matrices, n by n invertible matrices A and B. We can define the product, which is again an n by n matrix with the entries in R. Now what about the determinant? Determinant of AB is nothing but determinant of A into determinant of B. Since these two are non-zero real numbers, its product will also a non-zero value. This is not equal to 0. That means AB is also invertible. So given A and B in this set, this product AB will also lie in this set GLNR. That means the product operation is also is a binary operation on the set GLNR. Now, what if I am considering M of R? Okay, let us consider the set M of R. Here M of R is the collection of all real matrices. Okay, real matrices. Here we have no restriction for the order of matrices. There it consists of all possible matrices over R. So will addition form a binary operation on this set? Definitely no, right? Because if I am considering two matrices A and B over R with a different order, say A is of order 2 by 2 and B is of order some 3 by 4, we cannot define the sum. So the addition is not an operation, it's a binary operation on the set M of R. Similarly, multiplication for matrices of different orders, the multiplication is also not defined. So these are examples and counterexamples for binary operations. Now let us discuss some properties of binary operation. An operation, let S be a set and star be a binary operation on that set S. Now the operation star is called commutative if we have the property A star B is equal to B star A for every A comma B belongs to the set S. Okay, what are the examples for commutative binary operations? If I am considering the operation, okay, addition on the set N or Z or Q or R or C or Mn of R with C or Mn of R. In all these cases, the operation is commutative because this is addition, right? So given any two numbers, we know that addition is commutative. Given any two complex numbers A and B, we know that A plus B is equal to B plus A. That means addition is a commutative operation of all of these sets. Now what about MNR? MNR is the set of all n by n matrices over R. So, but we know that matrix addition is also commutative. Given two n by n matrix A and B, A by B is A plus B is same as B plus A. But what if I am considering GLNR with multiplication or MNR with multiplication? GLNR with multiplication. Multiplication is a binary operation on this set, but we know that matrix multiplication is not commutative in general. So this is not commutative operation. Now let us define associative binary operation. A binary operation is called associative if we have the condition A star B star C is equal to A star B star C for every A comma B comma C belongs to S. For any three elements A, B, C in S, we should have this condition. Then we say that the operation star is associative. What are the examples? I can take the same example. Addition on any of these set is again associative, because that we already know. Similarly, you can take multiplication on any of the sets N, Z, Q, R, M, and R. This will be a associative binary operation, because we already know that matrix multiplication is associative. Similarly, multiplication of numbers associative, etc. Now, next one is identity element for a binary operation. So, given a binary operation star on a set S, an identity element for this operation star is an element E belongs to S, satisfying the condition A star E is equal to E star A is equal to A for every A belongs to S. If there exists such an element, then we call it as an identity element for the binary operation star. What are the examples? If I am taking, if I am considering the binary operation addition on the set Z or Q or R or C, what will be the identity element? We know that 0 belongs to these sets, right? And also we know that for any number, n plus 0 is equal to n is equal to 0 plus n. So this satisfies the required condition. So 0 is an identity element for the binary operation addition for these sets. So similarly, if we are considering M and R with addition, it's a binary structure that we already know. So what will be the identity element? It will be the n by n 0 matrix. Because for any n by n matrix over R, we know that A plus 0 matrix is equal to A, which is equal to the matrix 0 plus A. Now we may define group. Here is the definition. Here is the definition. A group G star is a set G together with a binary operation star on G such that the following conditions are satisfied. The first property, for all A, B, C belongs to G, we have A star B star C is equal to A star B star C. Then we have already seen that this property is called associativity of star. And the second condition says that there is an element E in G such that for all x belongs to G, E star x is equal to x star E is equal to x. This is actually identity element for the binary operation star. And the third condition says that corresponding to each element A in G, there is an element A dash in G such that A star A dash is equal to A dash star A is equal to E. And this element A dash corresponding to A is called inverse of A dash with respect of inverse of A with respect to the binary operation star. So what is the definition says? the definition says that a group is a set together with a binary operation such that the binary operation must be associative and there should exist an identity element for that binary operation, and for each element there exists in an inverse with respect to that binary operation. Now let us see some of the examples. I'm considering all of these sets together. I'm considering the operation as the set is Z together with the addition, Q with addition, R with the operation addition. So I can consider set of all complex numbers. I may add this here. Set C with the addition. When considering these four sets, I will check the condition for group in a single step because they behave in similar manner. Okay. So what we have to check? First we have to check the closure property. First we have to check the closure property. And second, we have to check the associativity of the binary operation. Then we have to check the existence of identity. And fourth condition is the existence of inverse. The first property is already we have checked, right? So first property is closure property. That is, we have to check the operation addition is a binary operation on that set. We already seen that addition is a binary operation on the set Z, Q, R, and C. So first property is verified. The second one is associativity. We already know the addition of numbers is always associative. So the second property is also straightforward. And what's the third property? It's about the existence of identity element. What will be the identity element? For all of these binary structure, we know that 0 belongs to the corresponding set. The 0 belongs to Z, Q, R as well as in C. And it is satisfying the condition that for any element A plus 0 is equal to A is equal to 0 plus A. So 0 is the identity element for the operation addition in all of these sets. Now what about the fourth condition? Existence of inverse. What will be the inverse? For any number, the inverse is again an element of that set satisfying the property A star that number is equal to the identity element, which is 0 is equal to that element plus A. The only possibility is minus A, right? So for any element A, minus A will be the inverse. So inverse also exists. So these four forms a group under operation addition. Now what about this one? So these are all groups. What about n under addition? If I am considering n under addition, okay, closure property is already verified because addition is a binary operational set of natural numbers. Clearly, it is associative. And also, now what about the identity element? For any n, identity element is the number such that n plus that element should be equal to n. What is the only possibility here? The only possibility here is 0 element, but it is not in the set n. So there does not exist identity element for the operation addition. So this condition violates. Therefore, n under addition is not a group. Okay, now we may consider the operation multiplication. First, I may consider these two cases. So first one is R plus under multiplication and the second one is R star under multiplication. What is R plus? R plus is the set of all positive real numbers. Set of all R belongs to R such that R is greater than 0, whereas R star is the set of all non-zero real numbers. This is equal to set of all R belongs to R such that R is not equal to 0. So I have to check that these sets forms group under multiplication. First of all, I have to check the closure property. First, I am considering this R plus or given any two positive real numbers R1 and R2. You know their product will also a positive real number. That means multiplication is a binary operation on the set of positive real numbers. Similarly, given two non-zero real numbers R1 and R2, the product R1 into R2 is also not equal to 0. Therefore, multiplication is a binary operation in the set R star also. Now, already we know that the numbers, multiplication of numbers is always associative. So there is no need of checking the second condition. This is straightforward. Next, we may check the existence of identity. What is the possible identity for an element of the set? So given any positive real number or non-zero real number R, identity element is the one element of that set satisfying the property R into that element is equal to R. Is equal to that element into R. The only possibility is 1, right? Also, 1 belongs to these two sets. So, there exists an identity element for the multiplication operation in R plus as well as in R star. And finally, existence of inverse. For that, given any positive real number R, what will be the inverse? It's again an element, say R dash, such that R into that element should be equal to the identity element, which is 1, is equal to that element into R. What is the only possibility? This is 1 by R. Okay. So if I consider the set R plus, since R is a positive real number, 1 by R is also positive real number. That means that 1 by R belongs to this set R plus. Implies the x inverse exists for each element of the set R plus. Similarly, if R is a non-zero real number, 1 by R is also a non-zero real number. So this quantity 1 by R belongs to this set. Which implies every element of this set R star has an inverse. So these two sets are in both of these cases, the condition 4 is also verified. So these two are also examples for groups. Now, what about n under multiplication? If I am considering n under multiplication, okay, we have the closure property because multiplication is a binary operation. Clearly, it is associative. There exists identity element also. One is an element in element that satisfying the property that n into 1 is equal to n is equal to 1 into n for every n belongs to n. That one belongs to this set n. So there exists identity element. Now what about the inverse? We know that for if I am considering the number 2, the inverse must be equal to 1 by 2, right? If I am considering the number 2 belongs to n, the possible inverse should be 1 by 2 into 1 by 2 is equal to 1. But 1 by 2 is not a natural number. So it is not closed under inverse. So any number other than 1 does not have an inverse under this operation multiplication. So this is not a group. Here, fourth condition is valid. Now, what about R under multiplication? I'm taking these two examples together. So, multiplication is a binary operation on R as well as on C. Clearly, they are associative. Also, one is an element of R as well as C, which acts as identity element for the operation multiplication. So, we remain with the fourth condition. What about the existence of inverse? You know that for any non-zero real number or non-zero complex number, say Z, we have 1 by Z, which is again in that Z. So for any non-zero number, there exists inverse under this operation multiplication. But what about 0? 0 is an element of R as well as C. But 1 by 0 is not defined. Okay, or that does not exist for 0, that does not exist any element say R such that 0 into R is equal to 1. Okay, that does not exist such an element. That means 0 has no multiplicative inverse. Does not exist an inverse for the element 0 under this operation. So these are not binary. These are not examples for groups. Because the fourth condition is valid. Now, if I consider these two examples, this one is set of all M by N matrices over R. What is that? I'm considering M by N of R, set of all M by N matrices over R, and the operation considered is addition. Will this form a group? We will check one by one. Okay, first condition, the closure property. Clearly, given any two M by N matrices, A and B, their sum A plus B is also, if the, clearly the addition is defined, right? Because they are of same order. A plus B is again a M by N matrix and it has entries from R. So, addition is a binary operation on the set of all M by N matrices over R. So closure property is satisfied. The second one is associativity. We already know that matrix addition is associative. For any three M by N matrices over R, A, B, C, we have A plus B plus C is always is equal to A plus B plus C. So the second condition is also verified. Now the third one is existence of identity. What will be that? We can guess easily, right? So we have the zero matrix of order M by N in that set. Now for any element A belongs to M by N of R, we have A plus the zero matrix is equal to A, which is equal to the zero matrix plus A. So this acts as identity element for this operation in this set. Now finally, existence of inverse. So given an element A belongs to the set M by N of R, what will be the possible inverse? It will be minus A. Okay, if A belongs to this set, minus A will also be element, also an element of the set. What about A plus minus A? Plus minus A is equal to the zero matrix for the M by N, which is equal to minus A plus A. That means there exists inverse for each element corresponding to this operation. So from all this property, we can say that this set together with this operation forms a group. Now we remains with the one example, which is the GLNR, set of all invertible M by N matrices over R. So GLN of R. The operation considered is multiplication. So clearly it is a binary operation that we have seen already. So closure property is verified. And the second property we have to verify is the associativity. So since matrix multiplication is associative, the second condition is also satisfied. Now, the third condition is the existence of identity element. We already know that the n by n identity matrix belongs to GLR because its determinant is 1 and it's satisfying the condition that A into IN is equal to A, this is equal to IN into A for every A belongs to this GLN of R. So this matrix IN will act as the identity element. And the last condition is the existence of inverse. Now given any A belongs to GLN of R, since A is invertible, we can talk about the inverse matrix, right? A inverse, which is the adjoint of A by determinant of A. Now, what is A into A inverse? A into A inverse is the identity matrix of order n. This is equal to A inverse A. That is, for each element A in GLN R, there exists an inverse under this operation multiplication. So this set GLN R under this operation multiplication forms a group. So these are the examples. Okay, thank you.